Bienvenidos a la forma más entretenida de aprender y repasar matemáticas. Esto es Matemáticast con el profe Sergio Ruiz. Prepárate porque ya comenzamos un nuevo episodio.
Visita www.sergioruiz.com.mx y sigue al profe.
Welcome to the Deep Dive, where we take a stack of information and extract the most important nuggets of knowledge and insight, helping you get well-informed quickly. Today, we're embarking on a journey into a topic that feels almost like cracking some kind of universal code. We're talking about how abstract mathematical patterns seem to secretly govern, well, almost everything around us. From the tiniest particles to the grandest galaxies, and even the blueprint of your own body.
It really is a fascinating exploration. We're looking at the deep connection between concepts like, the golden ratio, Fibonacci sequences, attractors, symmetry, and how these ideas, these mathematical ideas, don't just live in textbooks. They actually show up in stunning ways all through the natural world and in human creations, too. You might find yourself seeing numbers and patterns in places you never really expected.
Okay, let's unpack this then. We've got sources ranging from sort of foundational definitions of these matter concepts, all the way to detailed analyses of where they appear in nature, in art. Our mission today is to show you not just what these patterns are, but maybe dig into the why. Why are they so prevalent? And what is that challenge about how we understand reality itself? Let's begin with a classic, one I bet many of you have heard of, the golden ratio. Sometimes called the divine proportion. Sounds kind of mythical, doesn't it? But at its heart, it's a very specific mathematical thing.
Exactly. Geometrically speaking, it's a unique proportion. Euclid defined it. Basically, if you divide a line into two parts, a longer part A and a shorter B, the whole length, A plus B divided by A, is the same as A divided by B. And that ratio comes out to about 1.618. It goes on forever. We call it phi. That's irrational, like pi. No repeating pattern in the decimals.
Right. And tied really closely to this is the Fibonacci sequence. Most people might know it from that famous rabbit problem, how rabbits multiply. It's a simple series. Each number is just the sum of the two before it. Usually starts 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. You get the idea. It goes on infinitely.
And what's truly remarkable is how they connect. If you take any number in that Fibonacci sequence, say 13, and divide it by the one before it, 8, you get 1.625. Now go further out. Take 89 divided by 55. That's about 1.618. The further you go, the closer that division gets to the actual golden ratio, to phi. This convergence, this relationship, is what gives the golden ratio its self-similarity. It looks the same at different scales.
Okay, so we have these, elegant mathematical ideas. But here's where it gets really compelling, I think. They aren't just abstract concepts locked away in math departments. They pop up everywhere in the natural world. It almost feels like nature's got a secret rule book based on these numbers.
It really does seem that way sometimes. We see it so clearly in plants. There's a whole field, phyllotaxis, that studies this. Think about the number of petals on a flower. It's incredibly common to find Fibonacci numbers, 5 petals, 8, 13, 21. You'll rarely find, say, 20 petals or 24. And this isn't just petals. It extends to how leaves are arranged on a stem, how trees branch, even how seeds are packed into a head.
The sunflower is a classic example, isn't it? I remember seeing pictures of that. If you look closely at the seed head, they form these distinct spirals going outwards. And if you count the spirals going clockwise and then counterclockwise.
You often find consecutive Fibonacci numbers, like maybe 21 spirals one way and 34 the other, or 34 and 55.
How does that even happen? Is it just chance?
It seems not. It's actually a brilliant example of nature finding an optimal solution. This arrangement is driven by something called the golden angle, which is about 137.5 degrees. It's related to the golden ratio. Using this angle for each new leaf or seed means the plant packs them in the most efficient way possible. It maximizes sun exposure for leaves or space for seeds, no matter how big the plant gets. It's incredibly efficient packing.
Wow. Okay, so it's optimization. But it's not just plants, right? You mentioned humans earlier.
Yeah, well, you have to be careful because some claims get a bit exaggerated.
Right.
There's definitely compelling evidence for golden ratio proportions in the human body. Things like the ratio of your total height to the height of your navel, or the lengths of the bones in your fingers. Even the cochlea in your inner ear can form a golden spiral shape.
And why would that be? Is there an advantage?
Well, one theory is about perception. Some researchers suggest our brains might process visual information more efficiently when it's structured according to these golden proportions. So maybe we find it aesthetically pleasing simply because it's easier for our brains to handle, an evolutionary thing perhaps, and it goes deeper still. It's even found incredibly at the molecular level. A cross-section of the DNA molecule shows relationships based on pentagons, which are directly linked to the golden ratio.
DNA itself, that's amazing.
And it is, and animals show these patterns too. Think about the sections of a bee's body, or the intricate patterns on a peacock's feathers, or the classic example, the spiral shell of a mollusk, like the nautilus. That's a logarithmic spiral, often approximating the golden spiral.
You mentioned bees. Is there something specific there?
Ah, yes, the bee lineage. It's quite neat. Male bees come from unfertilized eggs, females from fertilized ones. If you trace back the ancestry of a male bee, the number of ancestors in each generation follows the Fibonacci sequence, and the ratio of female to male bees in a hive tends towards the golden ratio over time.
Okay, so plants, animals, DNA. What about non-living things? Does it extend further?
It seems to. Some studies point to these ratios appearing in the dimensions of planets like Earth and the Moon, or the timing of planetary orbits. Definitely in the shape of spiral galaxies, those beautiful arms often follow logarithmic spirals related to phi.
But even things like hurricanes, those massive spirals.
Yes, the patterns in hurricanes often approximate these spirals too. It seems to be a preferred shape for swirling systems.
It feels like it's almost everywhere you look.
Well, people have certainly looked. There are discussions, some more speculative than others, about its presence in heartbeat rhythms, atomic structures, even things like predicting optimal temperatures for life or using Fibonacci projections in, say, stock market analysis.
The stock market one sounds a bit more controversial, maybe.
It definitely is. Those kinds of applications are much more debated than, say, the patterns in a sunflower. But it shows how far people have tried to apply these ideas.
Okay, so we've talked a lot about these static patterns like Foio and Fibonacci, but mathematics also describes change, dynamic systems. What about patterns in how things evolve over time?
Right. That brings us to concepts like attractors in dynamic systems theory. An attractor is basically a state or set of states that a system tends to move towards, kind of like a destination, regardless of where it started. Think of a simple pendulum swinging. Friction slows it down, and eventually it stops, hanging straight down. That fixed point is its attractor, a fixed point attractor.
Okay, that makes sense. Are there other kinds?
Yeah, there are other classical types. A limit cycle is another one. Imagine a thermostat controlling temperature, or maybe an old radio circuit tuning in. The system settles into a stable, repeating pattern or oscillation. That's a limit cycle. Then there's a limit torus, which is a bit more complex. It's like a repeating path, but governed by multiple frequencies that don't quite line up, so it sort of wanders over the surface of a donut shape, never exactly repeating the same loop.
The donut shape.
Okay.
But then I've heard of strange attractors. These sound, well, strange, more chaotic.
They are indeed linked to chaos theory, and that's what makes them fascinating. Strange attractors, like the famous Lorentz attractor, which came from weather modeling, describe systems that seem random but are actually deterministic. They follow rules. They have these incredibly complex fractal structures. If you zoom in, you see more detail, more structure, infinitely. The system never repeats the exact same state twice, but it always stays within a specific bounded region, tracing out this intricate pattern. It's attracted to that complex shape.
And looking at diagrams of strange attractors, they often look like these wild, spiraling paths.
Exactly. Which brings us nicely back to spirals. A specific type, the logarithmic spiral, is incredibly common in nature. It's also called an equiangular spiral or growth spiral. The key thing is that as it grows outwards, the distances between its arms increase geometrically by a constant factor. It keeps its shape as it grows.
How's that different from, say, the spiral groove on a vinyl record?
Good question. That's more like an Archimedean spiral, where the distance between the arms stays constant. Logarithmic spirals expand much faster.
And it's these logarithmic spirals that we see everywhere.
Very often, yes. It's genuinely mind-bending, isn't it? The same mathematical form, these logarithmic spirals, shows up in the arms of distant galaxies spanning light years, and in the swirling clouds of a tropical cyclone here on Earth. And even in the flight path a falcon takes when it zeroes in on its prey. It maintains a constant angle to the target, creating that spiral.
And back to the mollusks, shells, and sunflowers again.
And back to the shells and sunflowers. It really suggests there's some deep underlying mathematical principle driving how natural forms grow and how processes unfold. It's not just coincidence. There seems to be a fundamental efficiency or stability in these patterns that works across incredibly different scales and contexts.
It makes you wonder if it's like the universe's preferred way of building things or organizing complexity.
That's a great way to put it. A preferred method.
Okay, let's shift gears slightly. Talking about preferred forms, when we think about beauty, especially classical beauty, we often think of symmetry. From the ancient Greeks loving circles as spheres to the design of grand cathedrals, symmetry often feels like perfection.
Absolutely. And in physics, symmetry goes beyond just, visual geometry. A physical theory has symmetry if its equations don't change when you perform certain transformations like moving it in space or rotating it or mirroring it. The physicist P.A.M. Dirac had this famous idea. If a fundamental law of nature is mathematically beautiful, elegant, symmetrical, it's more likely to be correct. And a really basic symmetry people assumed for centuries was left-right symmetry or parity. The idea is that the laws of physics should be the same for an event and for its mirror image. The universe shouldn't inherently prefer left or right.
But nature is full of things that aren't symmetrical in that mirror image way, right? Like
Yeah.
Our hands, my left hand and right hand are mirror images, but I can't perfectly place one on top of the other. They're different. What are those called?
Enantiomorphs. And this property is called chirality, from the Greek word for hand. It's absolutely crucial in chemistry. Molecules can be chiral too. They can exist in left-handed and right-handed mirror image forms.
Like twins, but mirror images.
Exactly. And while these enantiomers have the same basic physical properties, same melting point, boiling point, their biological effects can be drastically different. The most tragic example is thalidomide. One-handed version was a safe sedative, but its mirror image caused horrific birth defects.
Oh, I remember hearing about that. Terrible.
It really was, and it highlighted this molecular handedness. Our bodies are chiral. For instance, our enzymes can typically only process right-handed sugars. Life itself has a preferred handedness.
Okay, so biology has this preference. But what about the fundamental laws? Does the chemistry just happen to favor one hand?
Well, that was the puzzle. When chemists synthesize chiral molecules in the lab without any guiding influence, they almost always get a 50-50 mixture of left and right-handed forms. Racemic mixture, it's called. But life processes, like how amino acids, the building blocks proteins, are formed and used, show this overwhelming preference for left-handed forms. For a long time, nobody knew why. Why would life choose a hand, and how could that preference arise if the underlying laws were perfectly symmetrical?
So what changed? How did they figure it out?
The breakthrough came from particle physics, surprisingly, with something dramatically called the overthrow of parity. In the mid-1950s, based on some puzzling experimental results with particles called chemosins, theorists T.D. Lee and C.N. Yang proposed that maybe one of the fundamental forces, the weak nuclear force, doesn't respect parity symmetry. It was a radical idea. But then came a famous experiment led by Qianxiang Wu using cobalt-60 atoms cooled way down.
What did they find?
They found that when the cobalt-60 nuclei decayed via the weak force, the electrons they emitted weren't random. They were preferentially emitted in a direction opposite to the nucleus's spin. If you looked at the mirror image of the experiment, the electrons would appear to be emitted along the direction of spin. The mirror image behaved differently. Nature, at the level of the weak force, does distinguish between left and right. It's not perfectly symmetric.
Wow. That must have been a huge shock.
It was enormous. The story goes that physicist Wolfgang Pauli, when he heard the results, famously said something like, "God is a weak left-hander," or perhaps, "God committed a mistake." He was stunned.
Reminds me of that Richard Feynman story. Didn't he have an analogy for this?
Yes. He compared it to visiting a beautiful temple gate in Japan, perfect in every way, except the architects deliberately carved one small detail upside down.
Why?
So the gods wouldn't get jealous of human perfection. Feynman quipped that maybe nature itself is only almost symmetric, so that we don't get jealous of its perfection.
I like that. A universe with a tiny, deliberate imperfection.
It's a charming thought. Of course, physicists didn't stop there. They looked for deeper symmetries. It turns out that while parity P is violated, and charge conjugation, C swapping particles for antiparticles, is also violated sometimes, the combination of C, P, and time reversal, T, together, CPT symmetry seems to hold universally, as far as we know. The laws look the same if you swap particles for antiparticles, mirror reflect everything, AND run time backwards.
Okay, that's getting complicated, but the main point is that simple left-right symmetry isn't fundamental.
Exactly. The discovery of parity violation was profound. It showed a hidden subtlety, a nuance in the universe's fundamental rules.
So bringing this back to human perception and creation, these mathematical ideas like the golden ratio haven't just shaped nature, they've shaped what we build and find beautiful.
Absolutely. For millennia, you look at ancient structures like the Parthenon in Greece or the Great Pyramid of Giza, and architects and artists seem to have used the golden ratio, either consciously or maybe just intuitively finding proportions that felt right.
And in art, too. Like paintings.
Oh, definitely. Leonardo da Vinci is famous for supposedly incorporating it into works like the Mona Lisa or the Last Supper, guiding the composition. We see it explored in sculpture and even claims about musical instruments like Stradivarius violins, using specific ratios for supposedly more harmonious sound.
Why do we find these proportions so appealing? Is it just cultural or something deeper?
Well, as we touched on earlier, the idea that our brains might process these golden proportions more easily is a strong contender. If it's easier on the eyes, easier for the brain to organize the information, maybe that translates into a feeling of harmony, of beauty, an evolutionary echo, perhaps.
And it's not just ancient history, right? It's still used.
Oh, yeah. Think about modern design. The dimensions of your credit card are often very close to a golden rectangle. Graphic designers use it, consciously or not. Look at logos for big companies. Apple, Twitter, Pepsi analyses often find golden ratio relationships in their design elements, influencing their visual appeal and balance.
So it has this enduring power, whether we realize we're using it or not.
Exactly. And this whole journey, really, from, the spirals in a tiny shell to the arms of a galaxy to the proportions of a logo, it brings us right back to that deep philosophical question that people have argued about forever. Is mathematics discovered or is it invented?
The big one.
When we find these same mathematical patterns showing up so consistently, so independently across the universe, from fundamental particle interactions to cosmic structures to life itself, even inside us, it really makes you lean towards discovery, doesn't it? It feels like we're uncovering a language that reality itself speaks, just as Galileo suggested that the universe is written in the language of mathematics.
Rather than us just creating a useful description.
Right. It poses the question, are these numbers, these ratios, these symmetries and asymmetries inherent properties of reality itself?
It really does make you wonder, doesn't it? If numbers possess this kind of profound, almost austere beauty, as some mathematicians describe it, and if they dictate so much of the world we can observe, what does that tell us about the true nature of reality? Are we just scratching the surface? What other hidden mathematical truths might be out there just waiting for us to find them? And how will uncovering them change how we see this incredibly beautiful, incredibly complex, and maybe mathematically elegant universe we live in?
Encuentra al Profe Sergio en todas sus redes sociales como Sergio Ruiz y en www.sergioruiz.com.mx. ¿Ya ves que las matemáticas no son difíciles? Sigue aprendiendo. Suscríbete y no te pierdas el siguiente episodio.